This is a set of multiple choice questions from AQA A-Level Chemistry. They are all past paper questions. They are all from the amount of substance topic. This is set 9 of these questions, and there are 5 of them within this video. I'm going to recommend that you pause on the question and try it for yourself before listening to the review. That way you get to see how you're progressing, what you still need to work on. So let's get straight to the first question. And on here we have a molecule. It's a hydrocarbon, so we know it's carbon and hydrogen only, and the fraction by mass of carbon is 9 out of 11. That means that the fraction of hydrogen is going to be 2. We want to know the empirical formula. So it is a straightforward empirical formula calculation. We build our table, we have our elements at the top, we have M, technically we have AR, the atomic mass, we have N for moles, and we have ratio. And then I start to put the figures in. My 9 and my 2 come from my fraction by mass of carbon and hydrogen. My MRs come direct from the periodic table. If I then work out the N's, I get 0.75C and I get 2 H's. I need the simplest whole number ratio. So if I do that, I can actually see here the easiest way to get to a whole number is to multiply both sides by 4. That takes me to C3H8. Correct answer, C. Next question. And this is a really quite common question. You'll see this in many of the multiple choice sections on this topic that have already been made, where you are working out the volume of gas produced. And it does rely on your knowledge of the ideal gas equation, that if we keep temperature and pressure constant, and we know that R is a constant, then volume is directly proportional to number of moles. So we can use mole ratios to work out the volumes that have reacted. So let's begin by doing that. We have a 1-to-1 ratio. 1 mole of Xe reacts with 1 mole of F2 to make 1 mole of XeF2. Now if I've got 30 cm cubed of Xe and 20 cm cubed of F2, I also know that I'm starting with no XeF2, but I can see that fluorine is the limiting reagent. That's what's going to run out first. 20 centimetre cubed of it will react with 20 centimetre cubed of the Xe, and that will make 20 centimetre cubed of the XeF2. However, the Xe is in excess. If 20 centimetre cubed of it has reacted, that means that we have got 10 centimetre cubed left unreacted. My total volume is the sum of this 20 and 10. 30 centimetre cubed. Correct answer is C. Next question for you to try. And once again, we're looking at titration calculations here. What do we need to know though? Well, we're dealing with sulfuric acid. You have to know that that's H2SO4. You have to know that it's diprotic. So actually, our molar concentration of hydrogen is more important than the sulfuric acid. I've got 0.1 moles of H plus to neutralise. Now let's go through each example. In KOH, if I use my concentration, I've got my concentration that I'm working out actually, and I'm going through and I can see 1 times 50 over 1,000, I've got 0.05 moles. And I've got 0.05 moles of KOH, and there's 1 OH minus in each KOH. So that's my number of moles of KOH. If I look at the next one, dealing with the concentration of KOH, well, our concentration is 2. We're multiplying by the volume, 100 over 1,000. That's 0.2 moles. Neither of those are correct because I need 0.1 mole to counteract the H plus of OH minus. On to the third one, and we've got here concentration multiplied by volume. We have 0.2 moles of barium hydroxide, but there's 2 OH minuses in each barium hydroxide. So my number of moles is actually 0.4. I can see here I've done concentrations through, just ignore that. We're talking about number of moles. And finally, barium hydroxide. I've got my 1 times 50 over 1,000 is 0.05 moles. That's not correct. However, there are 2 OH minus in each one, so I've got 0.1 moles of the OH minus to neutralise 0.1 moles of the H plus. Correct answer, D. Next question. And so this is quite a fiddly one. There's a lot of information to take on board. Sodium azide decomposes to make sodium metal and nitrogen gas, but the sodium then goes on to react with potassium nitrate to make more nitrogen gas. We need to know how many moles of nitrogen we will make from 2 moles of NaN3. Well, to start with, it's really simple. 2 moles makes 3 moles in the first equation. Starting with 2 moles, I've got 3 moles of N2. But then we've got an important distinction to make. 2 moles of Na, but I'm actually starting with 10 moles of Na here. Now, what I'm going to do to find my actual moles of N2 is divide all of the numbers in this second equation by 5, because that's what we would get if I use the 2 moles of Na that I've made. So that takes me 10 down to 2, 2 down to 0.4, 1 down to 0.2, 5 down to 1, and 1 down to 0.2. I'm interested in the moles of N2, which is 0.2. I made 3 here. I made 0.2 here. That means that I've made 3.2 moles of N2. I don't want moles, I want molecules. So I'm going to multiply that by Avogadro's number, which is provided. We do that and we get 1.93 by 10 to the 24. Correct answer is B. Next question for you to have a go at. And a relatively straightforward one. We have got a concentration, a volume and an MR. So we're going to find out the number of moles first using C and V. My concentration is 0.4, my volume is 50 over 1,000. That means I've got 0.02 moles of copper sulfate needed within this solution. Now, my number of moles is 0.02 and my MR is 249.6. Multiply those together and that tells me the mass that we would have, 4.992 rounded to 4.99. Correct answer is D. That takes us to the end of this series of questions. Thank you for listening and goodbye.